Welcome back, space enthusiasts. Today, we're diving deep into the latest findings from the James Webb Space Telescope, JWST, and what they mean for our understanding of the universe. Stick around as we explore how JWST has refined, but not refuted, our cosmological theories, and we'll uncover the one mystery that continues to baffle scientists. These galaxies are not just big, they're enormous, and their very existence so early in the universe's history is puzzling to scientists. They're so massive and form so quickly that they challenge our understanding of the cosmos. Press releases have hinted that these findings could signify a crisis in cosmology. Some experts argue these galaxies shouldn't exist at all based on our current scientific models. The JWST, primarily tasked with exploring these ancient cosmic behemoths, has brought us face to face with these mysteries. The revelations are both shocking and exhilarating, especially since none of our most advanced simulations, like the celebrated TG50 from the illustrious project, have predicted anything like them. Stay tuned as we explore how these findings could reshape our understanding of the universe and what it means for the future of cosmology. Despite their lesser size and dimmer light, these formations are incredibly significant. They're not just small and faint, they're rare, and their presence is challenging some of our established cosmic theories. As these little red dots started appearing in more observations, they hinted that we might need to rethink some aspects of the Big Bang theory or our current understanding of cosmology. In previous episodes, we've touched on how these findings initially seemed to contradict existing theories. However, recent research in 2023 has provided compelling explanations that align these observations with our broader understanding of the universe's evolution. These studies have illuminated much about these curious red blips, yet they leave us with lingering questions and at least one unsolved mystery. So let's dive deeper into what these little red dots are, what they tell us about the early universe, and how they fit into the cosmic puzzle. Join me as we unravel these mysteries and edge closer to understanding the grand story of the cosmos. Today, we start with an intriguing study led by Catherine Chosey and her team, part of the comprehensive SEAR survey, which investigates the evolution of the early universe. A major focus of their research has been on the peculiar little red dots and other unexpectedly bright galaxies that shine much more intensely than predicted by previous simulations. However, the real spectacle was not stars, but the accretion disks. These disks, swirling with fast-moving gas, generate tremendous friction, heat, and light, illuminating the galaxies far beyond normal levels. This extra brightness made it seem like these galaxies had far more stars than they actually did. From our distant vantage point, these galaxies, due to their extreme distances, shone with a deceptive light, mimicking star-filled skies. But upon closer examination by researchers, when these little red dots were accounted for, the cosmic puzzle pieces began to align. The controversies faded, and the observations started to match the predictions of modern cosmology. This discovery pointed to the presence of massive, perhaps even overly massive black holes at the centers of these galaxies, powering the accretion disks with fast-moving hydrogen gas. However, there remains a twist in the tale. Despite solving many mysteries, the total number of such galaxies observed is still unexpectedly high, almost double what was anticipated, hinting that our cosmic tale is far from over. Approximately 13.4 to 13.6 billion years ago, something extraordinary happened. The early universe, denser and more chaotic than today, seemed to have a unique knack for converting gas into stars at a breakneck pace. This led to the formation of galaxies in numbers that double what simulations had anticipated. But why were these ancient galaxies so prolific? Current theories suggest that the denser conditions of the early universe may hold the key. Unlike today's galaxies, which have reached a sort of equilibrium between the forces of gas contraction, which leads to star formation, and the explosive dispersal by hot gas emissions, the early universe operated under a different set of rules. We are still piecing together this puzzle, but insights from a pivotal paper suggest a fascinating connection to another study we'll explore, which might just illuminate why these galaxies were so adept at star making. Stay tuned as we delve deeper into how these findings could rewrite the story of our universe's formative years, suggesting that the cosmic scales of star formation were tipped in a dramatically different way back then. In a recent delve into the cosmos, the JWST Advanced Deep Extragalactic Survey unveiled two of the most distant galaxies ever observed, known as JWST 14d1 and D2. These celestial bodies were formed when the universe was barely under 300 million years old, providing us a rare glimpse into the cosmic infancy. Why are these galaxies so fascinating? Well, not only are they luminously bright, but they're also surprisingly large compared to other ancient galaxies. To give you some perspective, while they're giants among their peers from the distant past, they're still minuscule compared to the cosmic structures we're familiar with today. Led by Stefano Carani and an impressive international team, these galaxies were meticulously analyzed to uncover why they deviate so significantly from what we expected. The findings suggest that in the dense, young universe, galaxies like these had a harder time dispersing gas, which in turn allowed star formation to proceed unchecked. If you're curious about the specifics of this discovery and what it means for our understanding of galaxy evolution, check out the detailed discussion in one of our previous videos linked below. Join us as we unravel the mysteries of these brilliant beacons from the universe's formative moments. This galaxy isn't just a relic, it's brimming with dust, rich in oxygen, and notably, it's exceptionally bright. The burning question was, what's the source of this intense brightness? Could it be a black hole, or is there another cosmic phenomenon at play? After 10 hours of detailed infrared observation, the mystery began to unravel. Not a black hole, but vigorous star formation. This galaxy is a hotbed of activity, with new stars bursting to life millions of years after the Big Bang. These stars are not just forming randomly, they're igniting in bursts throughout the galaxy, much like the processes we see closer to home. The real twist came when researchers pinpointed a region around the galaxy, almost like a halo, far from the central core, which is ablaze with new star formation. This area, bright and bustling, is not centered around any black hole, but is a result of gas densities colliding and sparking continuous star creation over millions of years. Initially, we wondered if a black hole could be the source of this galaxy's incredible brightness. But after thorough investigation, the answer became clear. The light was not from a black hole, but from stars that have been forming continuously for about 100 million years. Even more astonishing, this ancient galaxy is filled with dust and oxygen elements that can only be created after several supernova explosions. This means that this galaxy, which formed just 300 million years after the Big Bang, has already gone through multiple generations of stars. These second-generation stars, rich in complex elements, are what's fueling the galaxy's brilliant glow. This discovery is groundbreaking because it challenges previous beliefs. Scientists didn't expect to find such complex star systems so soon after the Big Bang, but JWST has shown us otherwise. Yet, rather than upending our understanding of cosmology, these findings reinforce it. The Big Bang theory remains solid, with these discoveries painting a richer, more detailed picture of the early universe. As we continue to explore, we'll need to dig deeper into these surprising findings. But one thing's for sure, the universe is full of wonders that are just waiting to be uncovered. Stay tuned as we continue this journey of discovery. But here's the exciting part. This is just the beginning. Over the next decade, as the James Webb Space Telescope continues its mission, we're bound to uncover even more incredible insights and answers to the cosmos' most puzzling questions. So while we eagerly await these future discoveries, why not check out some of the previous videos linked below? If you're passionate about space and science, make sure to subscribe, share this with a fellow space enthusiast, and come back tomorrow for more mind-expanding content. The James Webb Space Telescope, launched with much fanfare, promised to bring into sharper focus the cosmos' most ancient galaxies. Initial data has sparked a wave of excitement in the scientific community, not for breaking our current cosmological models, but for reinforcing them with new nuances. We'll look at how these observations align with the Big Bang theory and what adjustments are being considered. One of JWST's roles has been to measure the Hubble constant, the universe's expansion rate, with unprecedented precision. Recent observations have shown discrepancies with previous measurements made by the Hubble Space Telescope. This segment explores these differences and discusses why they are crucial for refining our understanding of the universe's expansion. The JWST has provided stunning images of some of the most distant galaxies, offering clues about their age and composition. This information is vital for testing our theories about galaxy formation and evolution. We'll delve into what these early galaxies tell us about the conditions of the early universe and how they challenge existing models. Despite its successes, the JWST has also highlighted how much we still have to learn, particularly about dark matter and dark energy. These components constitute most of the universe's mass-energy budget and affect its expansion. This segment covers how the latest data influences our understanding of these mysterious forces. The final frontier that JWST aims to explore is the era known as the cosmic dawn, when the first stars and galaxies form. This period remains shrouded in mystery, largely due to the lack of direct observational data. We'll discuss how close JWST is to potentially unveiling this cosmic era and what hurdles remain. The Big Bang theory has been the cornerstone of cosmology for decades. With JWST's new data, scientists have been able to scrutinize this theory more closely than ever. While some thought the findings might challenge the very foundation of this theory, it has largely held up. However, JWST's observations have introduced new elements that could refine our understanding of the early moments after the Big Bang. This segment will explore how the Big Bang theory stands in light of JWST's revelations and what new adjustments might be needed to accommodate the latest data. One of the biggest surprises from JWST's observations is the unexpectedly high mass of some early galaxies. These galaxies appear more massive than predicted by current models, which raises questions about how quickly these massive structures could have formed after the Big Bang. This segment will delve into the implications of these findings, exploring how they might suggest new physics or unknown processes at work in the early universe. Cosmic inflation is the rapid expansion of the universe that supposedly occurred fractions of a second after the Big Bang. JWST's high-resolution data could provide insights into this period, which has remained mostly theoretical until now. We'll explore how JWST's findings might offer evidence for or against this inflationary period, and what it means for our broader understanding of the universe's birth and development. JWST has provided unprecedented views of star-forming regions in distant galaxies, revealing that stars might have formed faster and earlier than previously thought. This segment will explore the data related to star formation rates, discussing how it might change our understanding of galaxy evolution and the processes that drive star formation in the early universe. One of JWST's goals is to identify the first stars, known as population II stars, which formed from the primordial hydrogen and helium after the Big Bang. These stars have so far been elusive, but JWST's capabilities bring us closer to detecting them. This segment will explore the search for these ancient stars and discuss what their discovery would mean for our understanding of the universe's earliest epochs. Gravitational lensing, where massive objects bend light from objects behind them, has been a crucial tool in cosmology. JWST has used this phenomenon to peer even further into the universe, magnifying galaxies that are otherwise too distant to observe. This segment will discuss how gravitational lensing works, JWST's contributions to this field, and what it has revealed about the universe's most distant regions. Black holes, particularly supermassive black holes, play a significant role in the formation and evolution of galaxies. JWST's detailed observations are helping scientists understand this relationship better shedding light on how black holes might influence their host galaxies. This segment will explore the latest findings on this interplay and what it means for our understanding of both black holes and galaxy formation. The cosmic microwave background, CMB, is the afterglow of the Big Bang and a vital piece of evidence for cosmological models. While JWST isn't designed to study the CMB directly, its observations complement CMB data by providing detailed views of the universe's structure at different stages. This segment will discuss how JWST's findings relate to the CMB and what this synergy tells us about the universe's history. Quasars are incredibly bright objects powered by supermassive black holes at the centers of young galaxies. JWST has been able to observe quasars in greater detail than ever before, offering insights into their role in the early universe. This segment will delve into what JWST's observations reveal about quasars and how they might have influenced the formation and evolution of early galaxies. Beyond cosmology, JWST is also a powerful tool for studying exoplanets. Its ability to analyze the atmospheres of distant planets could help us understand the potential for life elsewhere in the universe. This segment will explore how JWST is contributing to the search for exoplanets, what has been discovered so far, and the implications for finding habitable worlds beyond our solar system. JWST's deep field observations have provided a glimpse into the formation of the cosmic web, the large-scale structure of the universe composed of galaxies, filaments, and voids. This segment will discuss how these early structures form, what JWST's observations tell us about this process, and how this knowledge helps us understand the overall architecture of the universe. JWST's ability to observe galaxies at various stages of their development allows scientists to study how galaxies evolve over billions of years. This segment will explore how galaxies change from their early, chaotic states to the more structured forms we see today, and what JWST's data suggests about the future evolution of galaxies in the universe. Dark matter, which makes up most of the universe's mass, remains one of the biggest mysteries in cosmology. JWST's observations might not directly detect dark matter, but they can provide indirect evidence of its presence through gravitational effects on visible matter. This segment will discuss the latest findings related to dark matter and what they might tell us about this elusive substance. Cosmic reionization is the process that made the universe transparent to light, occurring about 1 billion years after the Big Bang. JWST's observations are helping to shed light on this period by studying the first galaxies and quasars that contributed to reionization. This segment will explore what we've learned about this crucial era in cosmic history and how it shaped the universe as we know it. As JWST continues its mission, it will undoubtedly provide more data that will challenge and refine our understanding of the universe. This segment will look forward to the future of cosmology, discussing the most anticipated discoveries and the questions scientists hope to answer with JWST's help. We'll also consider how these findings might influence future space missions and the ongoing quest to understand the cosmos. The cosmic distance ladder is a series of methods by which astronomers determine the distances to celestial objects. JWST's precision is refining these measurements, especially for distant galaxies. This segment will discuss how JWST's observations are helping to recalibrate the distance ladder, improving our understanding of the universe's scale and the distribution of galaxies. While JWST isn't designed to detect gravitational waves directly, its observations can complement those from gravitational wave detectors like LIGO. By identifying the sources of these waves, such as merging black holes or neutron stars, JWST helps provide a more complete picture of these events. This segment will explore how JWST contributes to the study of gravitational waves and what this means for our understanding of extreme cosmic phenomena. Stellar evolution is a well-established field, but JWST's detailed observations of stars at various stages of their life cycles are offering new insights. This segment will explore how JWST is refining our understanding of how stars form, live, and die, including new findings on supernovae and the role of stellar winds in shaping galaxies. The intergalactic medium, IGM, is the matter that exists in the space between galaxies. JWST's observations are helping to map the distribution and composition of the IGM, shedding light on how it influences galaxy formation and the large-scale structure of the universe. This segment will discuss the importance of the IGM and what JWST is revealing about this often overlooked aspect of cosmology. Primordial black holes, if they exist, could have formed in the early universe and might account for some or all of dark matter. JWST's ability to observe the early universe makes it a powerful tool in the search for these mysterious objects. This segment will explore the concept of primordial black holes, how JWST is aiding the search, and what their discovery would mean for cosmology. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.